Hello, my name is Evan Fischel, and I'm going to be demonstrating me and Peter Foley's CMSE 417 overlay routing project. Peter already went over the routing functionality, building the routing table and flooding, and also two of the methods from part 2. I am going to be demonstrating the 5 other methods from part 2, which we have completed. Because we were a 2-person group, there are a couple things we still haven't finished and won't be finishing. That is to say the security extensions and also the subscribe method. So as a 2-person group, I think we finished somewhat more than 2/3 of the work, but less overhead with only 2 people, so it worked out. So what we have here are 4 CMD prompt windows on Microsoft Windows, and they're each going to launch a different instance of our routing program with a different node name, node 1, 2, 3, and 4. And they're communicating via loopback because they're all on the same machine and they're on different ports, which are specified in the config files. The topology of the network as specified is that node 1 is going to be connected to node 2, node 2 is going to be connected to node 3, and node 3 is going to be connected to node 4, node 4 to 3, 3 to 2, 2 to 1, but nothing else. So a message passed from node 1 to node 4 is going to have to go through 2 and 3, and that way we get some demonstration of the routing. I'm sure Peter went through a more complex topology when he was demonstrating Jockstra, but for simplicity for this demonstration, I'm going with a smaller one so we can have fewer windows, get through this more quickly. So here we go. I'll launch these, and all of these nodes are now running, and they are accepting commands. So we'll start off by demonstrating ping from N1 to N4, and we're going to send 5 pings with a 1-second timeout between them. And there you go. Ping success. Simple as that. So now we'll demonstrate trace route to N4. And that also worked. Total of 70 milliseconds to do that. I actually added some output on node 2 on the intermediate node, so you can see that the traceroute packet hit them on its way through, and it took 7 milliseconds to get to N4, and it took less time to get to each of the intervening nodes. That's round trip time. Alright, so now we'll demonstrate the FTP method, and to demonstrate the FTP method, we'll see the directory that we are inside of. We have a copy of the Ruby installer, which is 16 megabytes about. So that's a good size to send pretty quickly, but demonstrate our FTP functionality. So we're going to send a copy of it to N4, which is in the same place. We'll give it a different name, and we'll get a copy of it. So let's FTP to N4, and we're going to send the Ruby installer.exe, and we are going to call it installer2.exe. And it started, and it's going to take a little while. We should see installer2 appearing in this directory. There it is. It's FTPing. It's up to 10 megs, 11, 12, 13, 14. Almost done. There it is. Okay, so it sent it at 60,000 bytes per second. 60 kilobytes per second. So not that fast. That seems slow. And the slowness is probably due to some of the inefficiencies that we had in our program, but the FTP obviously works. We open the installer.exe, we will see that it is a perfect copy of the Ruby installer. And so, yeah, it works. Finally, we're going to demonstrate the post and advertise methods. So here we'll create a group called group1, and we will add ourself, node 3 and node 4 to that group. There you go. The message in the advertise, only one message is sent, and it gets forwarded along to each member of the group, and then back, rather than sending multiple messages out from the source. So what you can see is that it pops them off in reverse order of the list. So N1 went through node 2 and 3, but the source was N1 when it got to node 4 here. And so it got from N1, and the next one it's going to go to is N3. It got it from N4. The next one it's going to go to is N1. It goes back to N1. It goes, we're done. 3 nodes have been subscribed. And also we subscribed ourselves with no one to come after us. So now let's send a message on it using advertise. Advertise to group 1. The message is CMSC 417, and it failed. All right, back to that. I broke because I thought my program wasn't working, but it actually was working. It was just I accidentally did advertise twice instead of doing post the second time, and the syntax was wrong for advertise. So let us do it correctly this time. We will advertise group 1 to node 1, node 3, and node 4. Success, as before. And now we will post, which we did not do last time. We wrote advertise again. We're going to post to group 1, and we'll write the message is CMSC 417. And there you go. Okay, see, that time it worked because I typed it properly. So the message went to, it obviously did normal routing. It got to N4 from N1. N1 sent it that. And then it sent it to N3, the next node in the group. And then it sent it back to N1, the third node in the group. And then after all of them sent their ACKs, N1 also did the completion message delivered to 3. So that is the end of the methods that we have implemented. So now I'm going to show you a bit of our code to describe how we did fragmentation. So fragmentation is implemented mostly in message.rb, which is a bit of a Frankenstein of a wrapper class. When messages are created, they are originally created as fragment number 0, which is the final fragment. When they get sent out by the router here, if the message is too large to be sent, it calls message fragment and send, and it doesn't send that message. Instead, it goes back to message.rb, and it does fragment and send. So fragment and send breaks up the message based on the maximum packet size into n fragments, and it invokes the router with a different parameter, a fragmentation piece. So here it creates n fragments for each one, and the fragments have a fragment number, a final field, which is either true or false if it's the last fragment, and the payload, which would be a fraction of the original payload, the same destination ID and source, and force parameter. So when a message comes in, the first thing it's going to do is check if it's complete. The check complete method is up here, and the check complete method returns true if the final fragment is in and all the fragments prior to that are also in. So if it's complete, then it's going to call assemble payload, which is going to do string concatenation on the JSON fragments of the payload, and then return the Ruby map represented by the JSON. So then you get the Ruby map to process. And the execute payload method is going to get called, which is the thing that comes in and says, what type of message is this? What do we do? Basically does every single thing for interpreting messages. So that is how fragmentation works. It works seamlessly. It does not appear anywhere, but when we turned that on, the messages continued to work exactly as they did before, when we were only sending one fragment. So that is fragmentation. And that is the extent of this demo. So thanks for listening.